Awesome. Thank you. Yes, thanks for everybody attending my talk. My name is Stephen Cocke. We're going to talk about lightweight breast cancer detection models, parameter efficient fine tuning, and knowledge distillation, which I know is a mouthful, but hopefully this will make much more sense by the end of it. This talk surrounds the research that I performed to earn my doctorate degree in AI/ML at George Washington University. Yeah, let's jump into it. It's good to be back at my alma mater. I guess I got to point that way, huh? Oh, nope, it's the green button. All right, in full transparency, most of the courses I teach are over Zoom, so I don't usually do this in person these days, nor on a screen this large. So this is the agenda I'm going to try to stick to today. My goal is to tell a story that starts with a problem and ends with a solution. It's that simple. But on the way, I'm going to go over some core machine learning concepts that I think are important to understand in order to digest this research. Mainly it's for people in the crowd, such as my wife, brother, and dad, that don't think about machine learning every day like I do. So, and then I'll go over some of the methodology used in my research, the key findings, and hopefully if I've done a good enough job, this image on the right here will make much more sense. So the main motivation behind my research is pretty straightforward. Breast cancer is still a major global issue today. But more importantly, in my opinion, there are places in the world where it is more impactful in a negative way. And these places tend to have lower access to early detection tools. What I mean by that is if you focus on the two graphs here on the right, these are displaying that breast cancer rates and mortality rates due to breast cancer are disproportionately rising in areas of the world that are considered low resource or have a lower human development index. So really the question boils down to, how do we build and deploy lightweight computer vision models in order to assist healthcare providers or where there are a lack thereof in these types of areas of the world, but also it would just be beneficial in general for places that have limited access to computational resources, right? Maybe you can't reach a server somewhere to do some computation. So again, I'm going to start with some simple concepts and then we'll accelerate here. But so what is computer vision, right? For those of us maybe not so familiar, it's considered an AI technique that enables computers to interpret and extract meaning from images and video. If we focus here on I guess if you look at the image in the top left, just like most neural networks, right, the motivation behind this comes from how your brain works, right? There's different neurons in your brain that focus on different aspects of what you see, and that goes through your eye, whether you realize that or not. That's what's going on. There are three main computer vision tasks I just want us to be familiar with. The simplest is image classification or object classification in the top left of that quadrant, where we can assign a label to an image, right? That easy. One step forward would be object detection, right? Those are where we can incorporate bounding boxes. We can get a little bit more specific about where, what, and how many objects are in an image. And then there's image segmentation, which we can be the most specific with and do classification at a pixel level, right? I can say exactly what pixel belongs to what object, foreground versus background, sheep 1 versus sheep 2 in this example, etc. For the purposes of my research, I'm focused on image segmentation. Specifically, can I classify a pixel as being a part of a cancerous tumor or not? And that could be healthy tissue and background, right? Doesn't matter. So I won't go too deep into the weeds just for the sake of time, but in modern computer vision, there are two main model architectures. There's convolutional neural networks, referred to as CNNs, and vision transformers. CNNs depicted on the top right here, vision transformers on the bottom right. Really what I just want to take away from this slide is, there's a difference between a local first versus a global first when we talk about extracting features from images. CNNs focus on local patterns. Vision transformers focus on global relationships, right? There are much more advanced models now that combine both of these techniques, but when we get to talking about the student models that I've trained, I selected, these different backbones for my experiments, right? So I believe it was Andrew, Dr. Taylor, spoke about this earlier, right? But foundational models, what are they, right? They're these large general purpose AI models trained on extremely large data sets, typically using hundreds of GPUs, something that I can't do at home for the most part. And what they're used for is, think about ChatGPT, other large language models, right? They are really good at very generic tasks. Typically, you take these models and you do one of two things with them. You either fine tune them on a domain specific task, right? We can bend them to do something very specific that it might not be able to do in a general state. Or you take the knowledge from that large model and you distill it into a smaller model that might only be good at that one thing. The example I have here, the foundational model that I used in my research is the segment anything model developed by Meta. This is actually SAM3. I believe when I was completing my research, only 1 and 2 had been released. But as you can see, right, whether it's a video or an image, these models are designed to be prompted, meaning you can give it a point or a bounding box or even text now because it's multimodal and specify what exactly you want segmented out of the image. So another core concept here is parameter efficient fine tuning, or PEFT for short. It's actually a family of techniques, but it all boils down to enabling you to adapt one of these large pre-trained models like SAM on the previous slide. Again, ChatGPT is a common example I like to use, where you're only updating a very, very small subset of the parameters. It significantly reduces the compute and data that you need. You can iterate on experiments faster, right? And it's all a part of taking this large model and slightly bending it to do something more specific. The technique that is most relevant for today is low rank adaptation, or LoRA. That's what I used in my research. The whole idea behind it is I can freeze all the parameters in a large model, and then I can inject these small matrices in specific spots in the model. And then when the model is training, I'm only updating those matrices, right? So like 1 to 2% of the model size is what I'm adjusting. I can do it on a CPU. I can do it on a GPU. A single GPU, I should say. And then the final core concept I want to talk about is knowledge distillation. So knowledge distillation is a technique for transferring knowledge from a large, complex model, typically referred to as the teacher, into a smaller, more efficient model referred to as the student, right? So why do we do this? So say I've taken, a large SAM model. I have implemented PEFT, and now it's really good at, detecting breast cancers and mammograms. However, that model is still too large to be deployed somewhere that is low on resources, right? So this technique is employed to take a student model that's much smaller, much more efficient, and I do two things with it, right? One, I have it mimic the behavior of the teacher by looking at the teacher's outputs and taking a loss there, like what's the difference? Which can be done either with intermediate features, which I'll talk a little bit more about, or just the predictions that it makes. And at the same time, it's also looking at the ground truth training data, right? So it's gathering knowledge from both aspects. And then we can, we have a trained student model. We can take that and we can deploy it in places where larger models can't fit, or it's just not realistic. All right. So what did I actually do? So on the right here, this looks much better. On the right here is the overall methodology that I'm going to step through over the next few slides, right? So start with what's the data set, what were some of the pre-processing steps that I did, the teacher models that I selected from, how did I train them, et cetera. And then I select one model, and then I perform knowledge distillation. What are the different student models that I looked at, and what were the different distillation techniques? So the data set is the VIN-DR MAMA. It's in the bottom left over there. It's an open source data set. It has 20,000 images, although only 1,000 of them actually have cancerous masses, right? So there was a very skewed data set. The way I handled that is I just downsampled, the images that didn't have anything, and so I had an even distribution, right? It's on the BI-RAD scale. If you're not familiar, very briefly, a BI-RAD scale when you go in for a mammogram of 1 means completely fine. There's no reason to think you have cancer. BI-RADS 5 is, after a biopsy, typically, you unfortunately have a cancerous tumor or something similar. So anyways, on the left are the original images, right? That's what I got out of the box. Some sample annotations are at the bottom. I have, there's a lot of different classes in here, such as suspicious calcification, not just masses. So when I pre-processed images, I had to remove some of the text, like in the top left, you see that RCC, right? Things that the model might pick up on because it's white pixels. It might think that's a part of a tumor or some other tissue. So scrubbed it of text. I flipped all the images so that all the breasts were on one side. And any, images with white backgrounds, I essentially took the inverse of so that they all had black backgrounds and could make this as similar as possible. And then finally, this data set only provided bounding boxes for the tumors and any other, objects. So I actually used a model to generate the segmentations by prompting it with the bounding box, right? I said, this is the thing that I want you to segment. That is not the goal of what I performed. That's not very useful to a doctor if they have to look at it and find it first and then say segment this, right? So I want a model that's lightweight, that just takes a mammogram and tells me if there's a tumor there or not, and if there is, segment it for me. And then I did the classic train valid test splits, but I'll skip all that. A secondary goal of this research was to kind of look at different augmentation techniques on the data set just to see if I got any model performance, any increase in model performance out of it, right? So I won't define all these, but here's a visualization of it at least. So I wasn't just working with, the data out of the box. I applied some augmentations to the overall data set to see, to the human eye at least, right? This looks more obvious than maybe the top left, et cetera. But I'll tell you about the results when we get there. All right, so the teacher models. So I mentioned earlier, there's like 3 versions of SAM now. At the time I performed this research, there was just 2. So the base models that I used for my teachers were MedSAM and SAM2. MedSAM is based off the original SAM1 architecture, but a research group took that model and trained the entire thing, right, with a bunch of GPUs on medical imagery. Because out of all the SAM models, none of them had any medical imagery in their pre-training. SAM2 was kind of on the other hand, I wanted a model that had an updated architecture, a little bit heavier, a little bit more complex with no medical pre-training, right? So you can kind of see the juxtaposition between both of these models. They both, under the hood, they have a very, very similar architecture when it comes to the big pieces, right, which is in this table. They both have image encoders that take up over 90% of the parameters, so that's the heaviest part of the model. They both have prompt encoders because, again, these models are designed to be told where to look for the most part. So they have prompt encoders where you can send in bounding boxes, et cetera. And then they have very lightweight mass decoders, which I actually end up reusing. They're trained on different data sets, but they're very, very large. Let me think. Yeah, okay. So this lovely, crazy spaghetti graph is just a screenshot of, I tracked all my teacher training experiments and weights and biases. If you're familiar, it's an MLOps tool. Just wanted to give you a visualization. So when we're talking about what teacher models did I use, there's 4, right? There's 2 base models. There's MedSAM and SAM2. And then there are PEFT versions of these models, which I will just stick lore on the suffix of them. In the case of the parameter efficient fine-tuned versions, I freeze the image encoder entirely. I inject the LoRa matrices in there, and then when I'm training the model, those matrices are being updated in the image encoder, and then the decoder is completely trainable, right? So I'm training those 2 aspects of the PEFT models. In the case of the base models, the image encoder is completely frozen. I didn't have the resources to fine-tune that aspect, so I only trained the mass decoder. For those of you familiar with LoRa, I experimented with a few different ranks, 432, 128, and 512. Those, if you're not familiar, that's just the size of the matrix for the most part, right? So I experimented with different sizes, thinking like, if I make that matrix bigger, maybe the model will get better. And then finally, I just want to touch on, there's a lot of stuff going on here. So I experimented with different loss functions when training the teacher models. So I looked at focal loss, binary cross entropy, a dice score, and then a weighted combination of all 3 or 2, right? So I did a lot of hyperparameter tuning as well as experimenting with some of these loss functions. So the student models, again, there are 4 flavors. My thought process here was, all right, the image encoder is the issue. It's too big. So let's swap that out with smaller versions. Those versions are a tiny vision transformer small, tiny vision transformer large. So same model architecture, but one's bigger than the other. And then ResNet 50 and ResNet 101, which have the convolutional neural network backbones, right? So we're revisiting stuff we've learned earlier. I reused the decoder from the teacher, but I randomized those parameters so that it doesn't retain any knowledge from the previous training, right? Because it's so lightweight, I didn't want to make my own, so I cheated a little bit. But and then one thing I want to point out here is that the decoder in the SAM architecture expects 3 inputs from the image encoder as well as from a prompt encoder. Those are one image embedding, and 2 high resolution features, right? They're of different dimensions, which are highlighted there. The student encoders that I chose don't output those features at those dimensions. So I had to add trainable projection layers. So when I'm doing this student model training, image encoder, the additional projection layers, and the decoder are all trainable at one time, right? I'm training the whole thing. This got cut off a little bit, but there are 3 knowledge distillation techniques that I looked at. A combination of mean squared error between the teacher and the student outputs, aka the logits, plus a binary cross entropy on the student mask versus the ground truth. Something similar with KL divergence, and then a 2-phase where I actually took a loss between this middle portion, the image embeddings and the high resolution features on the training set between the student and teacher, as well as on the outputs, right? So that's what's referred to as the 2-phase. I'm gonna spend a minimal amount of time on this slide because I think most of us are familiar with the classic evaluation metrics that are used across almost any machine learning project. Some on here are specific to computer vision, like intersection over union and diced. But there's 2 things I wanted to focus on. One is I used the McNamar test at the end of this. If you're not familiar with it, it's a statistical test to compare the performance between 2 classifiers, right? So I can say, was my teacher and my student, was there a significant difference in their performance on this data set or not, right? And I use that again and again for different models that you'll see here shortly. The second thing is, in order to get to, did my model miss or, false positive, true negative, right? In order to get that confusion matrix, I have to take the mask and do some calculations, right? So you'll see I have different intersection over union thresholds as well as pixel counts, right? Because, if my model outputs a bunch of sparse pixels all over the place, right, those can total up to say it missed the tumor, or it said there was one when there wasn't, right? So I enacted some metrics in order to get to a matrix. All right, the exciting part. So teacher model results first. I'm going to focus on the line plot in the top left initially. So this is showcasing a few different things, right? So the different colored lines are associated with the different teacher models that we talked about. The y-axis is the F1 score on the test set. The x-axis is the different loss functions. So the first takeaway here, and I got them down here if you'd rather read them, is that the SAM2 base model, a non-PEFT version, outperforms every model across all the different loss functions, right? It is just better, has a better performance. Next to that is the combination of BCE loss plus a weighted dice score also saw the highest performance across all the model types, right? Insinuating that loss function is probably the best even on models that probably I didn't experiment with. In the bottom, and again, that's the thresholds, right? The IOU threshold of 0.3 or 0.5, like how well did the mask overlap with the ground truth, as well as the threshold for keeping pixels, right? Because at a pixel level, my model is going to say, oh, I'm 40% this pixel is a part of a tumor, 40% confident, 50% confident, et cetera, right? So I have different thresholds where I measure how my model performs as I play with those. And the bottom left is, I think, the only graphic I have talking about how the models performed on the different augmented data sets, right? So unaugmented is at the bottom. I tried to circle the highest performing model, which is SAM2. But interestingly enough, at least from my use case, the unaugmented data set across model types, the model performed just as well on that data as any other augmentations, either just as well or better than, right? So if we look at the model leaderboard, the model that I chose for the knowledge distillation process was the base 2 SAM model on the unaugmented data, right? Pre-processing aside, that's always there. One more slide on the results of the teachers. So the box plot on the left is just looking at all of it, right? I did a lot of experiments. I didn't just train each one of these models once. I took a look at all of the experiments when it came to the parameter efficient fine-tuned versions of these models, both SAM2 and MedSAM, and said, hey, what happens when I increase rank, right? Do I need to be increasing it even more? So the only thing that I could really pull out of this as a result was that, other than those models don't perform as well as the base, is that the distribution of the results does seem to tighten up as we increase the size of the rank, right? So there's more variability in a rank of 4 across all these experiments with different hyperparameter settings, which is an interesting finding. But overall, in general, the mean, at least up to 512, did not change across experiments. Let's see, is that it on this one? Oh, and then I do include, right, the parameter count up here, just out of curiosity. Obviously, as I add more parameters through matrices and those sizes increase, the number of parameters are also going to increase. And this is a visualization of what this looks like, right? So some more key takeaways. On the left is SAM2 versus its PEFT version, MedSAM on the right. Something I did note was that when I do inject LoRa into MedSAM, the masks that are output definitely are cleaned up a bit, right? So if I draw your attention to the bottom right here, same test image, MedSAM LoRa. In the middle column is the ground truth, and then on the right is what my model predicted. MedSAM has a little bit messier. It might be picking up some of the healthy tissue as that's a part of a tumor. Whereas MedSAM LoRa cleans that up, much more. But MedSAM in general, base MedSAM had the highest number of false positives, which you can kind of see above a display of that. And then the student models, probably the most interesting part of this work, in my opinion. So again, line plot, 4 different models, Vision Transformer, large, small, ResNet, and ResNet 101. Across the board, the larger of the 2 Vision Transformer student models perform the best, followed by the smaller Vision Transformer model, which has the least amount of parameters. And then the convolutional neural networks lagged behind a bit, although it's not terrible performance. The parameter count is at the top, which I think is really important to take note of. You can see percent of teacher as one of the columns, right? So all these models, the biggest one is at 20% of the size and the smallest is at 4%. This is the model leaderboard here on the right. Red box is just to show you the top performers. This is sorted by F1 score, right? There could be an argument made that maybe recall is the most important, but I just based it off of F1, right? We would rather make sure that we catch it or say there's a tumor when there's not versus say there's not when there is one, right? But I guess that's up for debate. But anyways, this is sorted by F1 with the large Vision Transformer using the 2-phase distillation process as the highest performer, right? And we can also gather that from the line plot. On the far right is the 2-phase, right? That is typically the highest performer associated with the highest performers for the student models. And then I think I might have failed to mention earlier, the scratch BCE refers to, I also trained every student model from scratch on the data set without teacher guidance, right? I wanted to see how they performed, is knowledge distillation worth it? Here's a visualization of this process. This is specifically looking at the highest performing student models of one flavor, that flavor being the large Vision Transformer, right? So 2 phases at the top, KL divergent, MSE logits, and then the from scratch model on the bottom. This is the test image. You can see that the scratch and the third version of knowledge distillation failed to really capture that accurately. And then the top two nailed it. And then I believe this is the last slide of my results. So the biggest takeaway that I could possibly give is this table in the top left. You have the teacher model in the top row, the SAM2 model with its large parameter count, and then you have the best performers of the different student models below that. And we can see that the large vision transformer and the small vision transformer at 11% and 4% of the size of the teacher either outperform or perform pretty much just as well as the teacher, whereas the from scratch model did not, which insinuates that knowledge distillation does have an impact and can have an impact. The McNamar results are on the right. If you recall, this is just testing, do I have two different performers, two different classifiers on the same data set or not? So I look at this from the aspect of the teacher versus the student model from scratch, right? The vision transformer large from scratch. And yes, this test resulted in, yes, there is a significant difference between these two models, right? So they are different. They perform different on this test. If you look at the numbers, we can see that the teacher model outperformed the student. The teacher model versus the two-phase, which was the best of all the student models from the vision transformer large perspective, there wasn't a significant difference except at one IOU and pixel threshold. And if we tally up the numbers, it's because the student did better than the teacher. And then finally, if I look at the student model two-phase versus the student model from scratch, there is a significant difference across all the thresholds, right? Saying that the knowledge distilled student does in fact outperform the model from scratch. And then as promised, here's the image from the agenda slide. Hopefully this makes a little bit more sense, but to pull it all together, I have the teacher model on top. I have the large and small two-phase distilled models on the bottom. This is a test image where I don't know, just makes me feel warm and fuzzy inside that they nailed it. So with that, I will just leave this up on the conclusion slide for the sake of time. And thank you all for listening.
Right, thank you so much. Again, this room's running a little late, so if you're trying to get to one of the other talks, probably hop up and head to the other room now. But we have a little bit of time for questions while we swap out the speakers. Yeah, you want to go up there? I think they might be able to use your computer up there if you want to do that.
Right.
Yeah. All right, I'll walk around with the mic for anyone who has got questions. Put your hand back up, whoever was. Here we go.
So what did you do for data pre-processing? Because X-rays, let's say like if it's a standard X-ray or digital X-ray, you have different gradients, different signal to noise ratios. How did you handle that on the training set and then on future test sets?
So at least for this research, I'm in full transparency, I probably wasn't concerned with the future data sets. I believe when I took calculations, there was not a high signal to noise ratio. So I did, if I recall correctly, I did perform normalization, right, on all these images just to keep them within the same range. I think to answer that question, that's probably the biggest thing that I did, other than scrubbing them and trying to make them as normalized as possible. Yeah. Sorry, I can't see.
Cool. Any other questions we got? All right, let's thank the speaker again.
Thank you.